It's my pleasure today to introduce Professor Russel Dupuis from Georgia Tech University. He is one of the well-known architects of the use of MOCVD technology in optoelectrical devices. He was the first to actually demonstrate the use of this technology for things like LEDs, laser diodes, solar cells, and so on. Professor Dupuis was a member of the technical staff and a distinguished member of the technical staff at Bell Labs. He was appointed a chair professor in electrical and computer engineering at the University of Texas in Austin in 1989. In Georgia Tech, he started there at 2003 as a professor in electrical and computer engineering and material science. And he was the newly established Steve Chaddick Endowed Chair in Electro-Optics and a Georgia Research Alliance eminent scholar. He has received the National Medal of Technology in 2002, the IEEE Edison Medal in 2006, the Charles Stark Draper Prize of the National Academy of Engineering in 2015, among many other accolades that attest to his international status. So without further ado, please join me in welcoming Professor Dupuis.
Thank you very much for that kind introduction. It's a pleasure to be here at KAUST and to see so many of my friends, people I've worked with and know. So thank you for this warm welcome. And thank you for the cool welcome, because I understand it's relatively cool out today. Coming from Atlanta, this is a little warmer than our normal summer day. But I spent 14 years in Austin, Texas, so there were many times when I was out mowing the grass and it was 115 degrees Fahrenheit. So I'm familiar with this kind of environment in some respects. Today I'd like to talk a little about our work on MOCVD, but I'm going to focus largely on a bigger picture, the impact of this technology on the world and how people live today and how people communicate. As you know well, you have a group here that's going to be using MOCVD for research, and it continues to be a very important research topic. Let me go to my first slide, which is an outline. I'm going to talk, as I said, about how this technology developed very briefly, some of the things that happened historically that created the internet, which now depends entirely on MOCVD-grown devices for virtually all of the information transfer you're used to having access to at your fingertips. And then talk about the impact we have on lighting, how people use light and live their lives now based on solid-state lighting. I'm going to talk about specifically telecommunications, high-speed optoelectronics, and something that Saudi Arabia may be interested in the future, solar cell, solar power generation. And finally, talk about RF power, which you use in your cell phones, and then lighting. So let me begin with this. The picture's missing. This slide. It was supposed to have a picture of how Manasseh Vet. Dr. Manasseh Vet is a chemist working at the North American Aviation Laboratory in Anaheim, developed metalorganic chemical vapor deposition in 1967. So 50 years ago, this technology was born out of an interest in chemistry and the growth of semiconductors on insulating substrates. It's an interesting story about why he was interested in growing semiconductors on insulators like sapphire, but nevertheless, that was his primary interest. It wasn't an accident. It was specifically the technology he was trying to develop. For many years, that technology languished because other options for 3-5 semiconductors existed that were more well developed. But in about 1977, so 4 years ago, that changed. Along the way, I designed and built this reactor, which was rather conventional in many respects, but rather different in other respects. Nevertheless, this is what we started off with for MOCVD, a quartz chamber with RF heating, single wafer geometry. Looked like that up close. This is actually a sapphire wafer, sapphire single crystal alumina that is oriented on the basal plane, 001 plane. The reason it's an oval is the crystal itself was grown on a different plane and sliced to reveal this 100 plane. We had one gallium source, one aluminum source, and one zinc source for p-type doping. Arsine, we were growing gallium arsenide and aluminum gallium arsenide, and hydrogen selenide was our donor dopant. So this is where we started, and when I started this technology 40 years ago, this was state-of-the-art, actually, and you couldn't buy an MOCVD reactor. You had to build it yourself. That was true for virtually all of the technologies we were using for epitaxy at the time. Later on, 25 years ago, this was a commercial reactor that was used for production. So things really didn't change too much. Single wafer, still 2 inches. A little more exotic in terms of its gas switching. This is a gas switching manifold. Water-cooled, RF-heated chamber. So not much has evolved in that period of time. If you had seen the first slide, you would see how Manasseh Vet standing by his reactor, which was quite different. It was made out of Pyrex. And a lot of chemistry-looking things hung on it. So we've gone from Pyrex chemistry type tools to very complicated things. Then in 1991, another advance took place. I'm skipping a lot of advances, but this is another one I'm going to point to because Nakamura, working in Japan, working virtually alone in the Chia, developed a different style chamber that was a so-called two-flow reactor. And you see a schematic of it here. This was a single wafer reactor used for growing gallium nitride and was unique in some respects, but very common in others. Nevertheless, he was able to show for the first time that he could make a p-n junction in gallium nitride using magnesium as an acceptor and doing thermal activation to create the active acceptor states in the semiconductor. And that led to the first blue LEDs that were commercially available and to InGaN alloy quantum wells that we all now rely on for solid-state lighting. Today, this is what you would buy if you were in the business of MOCVD for solid-state lighting and other technologies. Obviously, much larger tools. Here's a picture of a wafer load being put into the chamber, multiple 2 and 3 and 4 and 6-inch wafers, and basically room-size epitaxial tools costing several millions of dollars. And here's a close-up of one of these chambers. These are 5 8-inch wafers in this reactor. So there's lots of improvement in our technology to improve the scale, improve the cost effectiveness, to improve the yields, but basically the same chemistry that Hal Manasseh Vet created in 1967. So 50 years, nothing's changed fundamentally. So it's good for you students here in the audience to understand the fundamentals of what's going on because the rest is details. Obviously, when you're doing your PhDs, details matter a lot, and inventing new devices or new approaches is important. As you all know now, this is a commercial product that you can buy. So in principle, it's like buying a car. You buy a car, and once you learn to drive, you can go anywhere you want. Not quite that simple. So people have to learn how to drive a car. There's lots of cars on the road now. This is a plot of an older slide, so 2015, the known MOCVD reactors in the world and where they're located. The biggest concentration that we know of is Epistar. They have over 450 MOCVD reactors at one company. What's not on this slide is the unknown number of reactors at Nichiya in Japan, which could be even larger, for all we know. But as you can see, largely this technology has moved into Asia. And in fact, there are two US-based companies here, Cree and Lumileds, and the rest are outside the US and belong largely to Asian companies. So this technology invented in the US has moved throughout the world now and pretty much is dominated by extremely large companies making light-emitting diodes. That isn't to say that MOCVD is only useful for making light-emitting diodes, as I'll show you. 25 years ago, when that Nakamura result was reported, this is what was going on in the world. Something close by here. The first Gulf War ended. Gorbachev resigned, the Soviet Union collapsed, and the new Russia was formed. Boris Yeltsin, for the first time in history, there was a free election in Russia, and he became the president of the Russian Federation. In South Africa, close by this environment again, the apartheid sanctions ended. Japan, unfortunately, had a very bad accident with Tokushima, which we're still suffering from today. Hubble spacecraft is launched, but you may recall Hubble had a design flaw and was inoperable when it was first launched, and they had to put eyeglasses on it to correct the vision of that telescope. And this is the important thing I want to get to. A guy named Tim Berners-Lee introduced the first web browser. This is all happening when Nakamura is designing his reactor and finally getting a blue LED. So as you can see, a lot of things have changed since 1991, 25 years ago. This is how the internet has grown. So we can draw analogies to solid-state lighting, but this technology didn't even have a number out here. But as you can see now, this is a projection made a few years ago. But you can see now there's lots of internet users. Some of you are in this audience. Maybe all of you are in this audience. And here's how the penetration has changed from 2014 to projected 2020, with the percent of the population involved in internet use from 41% to 54.6%, and users in billions of users up to over 4 billion users. So how did this happen? This is from 1991 to today. How did this happen? Our world has changed dramatically. If you go back, of course, to 1900 and look to 2020, you can see lots of big changes. But this is astounding. This is a change that society has yet to really fully digest, actually. People start worrying about how our children will learn. How will they interact with each other? Will they be focused on screens and not even know there's a neighbor sitting next to them? You can see this in the restaurants when you go, you watch people and they're on their phones. They're not having a discussion with their friend. Possibly they're looking at, the scores of some soccer game or something. And this is how things have changed really recently. This is internet users in 2011 and in 2017, just a few months ago. The thing you notice, although the colors have changed, this segment of Asia goes from 44% to 49.7%, and the other slices are reduced. So the number has grown, but the percentage has dramatically increased in Asia. And just like I showed you in terms of MOCVD reactors in Asia, the usage has largely expanded in Asia and continues to do so. This is the saturation rate for internet use and penetration rates and the total numbers, again, this year in June. And you can see where this usage is, and the average, world average is 51.7%. So there's still a lot of growth yet to be accomplished in terms of internet access and the transfer of information. As you all recognize, not all internet use is informational. In fact, probably a small fraction of it actually has to do with learning, and the rest is wasted time. So it will have a broad impact in society is what do we do with our wasted time? Do we actually become better humans, smarter, more efficient, more effective, more empathetic, more useful as humans? Or do we become sort of isolated bubbles of wasted time? So internet has two possibilities, right? It could be the death of society, or it could be a boon to society. It's up to you to determine that. Here's the cost and value of this to the world in terms of how much they're willing to spend. Total population, urbanization is 54%. Internet users is 50%. As you saw, in some societies it's less, some more. Penetration of social media is 38%. Unique mobile users, 66%. And active mobile social users, 34%. But the billions of dollars adds up to an incredibly large amount of money that's involved in this use of this technology. Again, this is something that happened since 1991. It's almost like something bigger than the car industry happened in a few years. So it's an incredible change in the way our society operates. Let me look back at how this happened. Well, this is 30 years ago. 30 years ago, the first transatlantic cable was laid across the Atlantic that used fiber optics. So not so long ago. TAT-8, it was called, Transatlantic Telecommunications number 8. It was the 8th cable laid. It only cost $335 million, and it retired from service in 2002. Why did it retire from service? Did it break? Was it worn out? No, it wasn't good enough in 2002. So they just abandoned it. It's still on the ocean floor, down there somewhere. Someone 100 years from now will dig it up and pull out parts, and it'll be in a museum, I suppose. One of the interesting parts about this is they're laying practice cables in various parts of the world, including the Caribbean and near the US coastline. And they found that the biggest reliability problem they had was from shark attacks. So this cable is an optics cable, but it has electronics in it. It has power cables running the entire length, because there's a repeater every 40 kilometers. So on the ocean floor, there are repeaters every 40 kilometers. Signals go through those wires that are electronic. And the sharks would pick up those signals and think it was food and attack it. So the cables were routinely being attacked and destroyed by sharks near the coastlines. They had to pull them up and repair them, but they had developed shielding for the sharks. That was really when I was at Bell Labs, that was the biggest problem they had, is shielding for shark attacks. So those of you who know about the Sharknado movies, something like that was going on. The first transatlantic cable to use fibers contained 2 working pairs of fibers, with a third as a spare. And as I mentioned, about 40 kilometers of cable, every 40 kilometers they had a repeater. Why was that? Well, because the fibers weren't good enough. They had optical loss, and so the signal transmitted down the fiber would decay away, and they'd have to regenerate it. Today, this is what's in the ocean floor, on the ocean floor. These are cables that are been laid over the course of the last few years. You see from 1991, we've gone from 1 cable to hundreds of cables connecting all of our continents. And here's how that usage goes. So you can see there's a lot of traffic in the Atlantic, a lot of traffic in the Pacific, and a lot of traffic within Europe. So this is really a game changer for how people communicate throughout the world. It used to be a big deal for the White House to have a phone that connected to the Kremlin. That was a big deal. So you could pick up the phone and call Khrushchev, right? Kennedy could talk to Khrushchev during the Cuban Missile Crisis and say, we're not going to bomb you, just take your missiles out. Okay, we'll take our missiles out of Europe, you take your missiles out of Cuba, everybody's okay, all right. So nowadays, nobody thinks about dialing Moscow as a big deal, right? Direct dial to anywhere, practically. So that's a big change. Another big change that's coming is fibers are coming to your home. Fibers are coming everywhere. So you won't be connecting through some cell tower to your home. You'll be connecting to a fiber system. Fiber to the home is a big deal. In Korea, in South Korea, there's lots of fiber to the home. In Atlanta, it's not so common, but it's coming. This is very high-speed internet access, and it's all premised on MOCVD-grown devices, entirely dependent on silicon, of course, but silicon is a dumb material until you connect it to 3 5s, then it becomes pretty smart. You can actually transmit information much more rapidly than RF, much more efficiently than RF. And we all talk about this, and someday it will be here, Internet of Things, where your refrigerator will talk to you and your cell phone and say, please bring some milk home. You're running out of milk. Your car needs to be charged. Your baby just wet her pants. You know, those kind of things will happen to you. You have smart clothing that will adjust to the heat when you're outside and change color when it gets dark so you can be seen. Fiber to the premises is here in some cities and some countries, as you know. There's something called a gigabit passive optical network running at 2.5 gigabits a second, moving rapidly to more advanced, more high density transmission systems. And GPON all right now uses 1490 lasers transmitting downstream and 1310 transmitting upstream. And if TV is involved, it's 1550 nanometers. These are all indium phosphide MOCVD grown laser diodes and detectors that are operating this Internet of Things and the internet you touch today. So without MOCVD, you take away that technology. Maybe it doesn't go away, it just gets 10 times more expensive and 10 times less accessible. This is what's in the Internet of Things and the current technology for Lightwave Systems. This is an optical photonic integrated circuit. It's a most advanced semiconductor optoelectronic circuit in the universe, as far as we know. I keep saying except for what the Klingons have, but if you're not a Star Trek fan, maybe the Klingons doesn't mean anything to you. But the Klingons have other things we don't know about, like cloaking devices and all that. So they probably have had this long ago. This is an MOCVD-grown wafer that's been processed for one of these. This is a stack of substrates that are ready to go in the epi tool. And here's the epi tool. And this epi tool shows a human hand reaching in through a glove box to load and unload the wafers. That's an old-fashioned thing. Now it's all robotics. So there's a stack of wafers in a cassette like this that gets loaded, and the robots handle everything. This is in the case for silicon technology. What do you actually need to make one of these photonic integrated circuits? You need to grow multiple growth runs of MOCVD materials. You need to do lithography and processing in between each run. So you could end up with stacks of epi that may be 4 or 5 levels of epi. Here's an example of a discrete feedback laser. And here's a buried quantum hole laser. Here's a schematic of that. These are done in multiple growth runs. So MOCVD tools are optimized for each one of these portions of the device. And ultimately, you end up with that photonic integrated circuit with 500 lasers on a single chip, each operating at a different wavelength. And this shows you schematically what's happening, at least. There's a chip that's the transmit, a chip that's the receive. And this has 500G capacity, has over 600 optical functions integrated on a single chip. and over 250 fiber connections eliminated by using integrated optics and photonic integrated circuits. The scaling of this versus time has approximately that of Moore's law for silicon, which I'm sure many of you are familiar with. So there's an optical version of Moore's law, which we actually call Heitz's law after Roland Heitz, who was a Hewlett-Packard leader who invented that plot just as Gordon Moore did at Intel. In 1991, when that Nakamura result and the Gulf War ended, this is what you had if you had a portable cellular phone, something like that, or this. This is 1983, the Dynatac, Motorola Dynatac 8000. This was state of the art. If you were James Bond, you had one of these. It's a big brick, obviously, and it's not something you want to keep in your pocket. It probably lasted a battery life of a few hours as well. And then this happened in 1991. That was from 1983. Nokia had the first GSM phone, this thing that you may recognize. And this is the Motorola version. They both cost around $1,000. So this is $400, this is $1,000. Today, of course, an iPhone X will cost you $1,000. But which would you rather have? It's pretty clear what you'd spend your money on, unless you were a museum, maybe you wanted to have one of these. So what has caused that to change from a $1,000 thing you wouldn't want to carry to the world's most advanced portable communication system? Again, it's the MOCVD devices that have allowed this transition to occur. I show you here the iPhone line. There's obviously the Samsung line and all these other companies' lines. But they all rely on something that is based on MOCVD, and that's the power amplifier. There's an RF power amplifier in each of these phones, or multiple ones actually, depending on which band you're using. And that is entirely grown by MOCVD. So sure, there's silicon, there's a display, there's actually all these have LED lighting on the backlit LCD panels. iPhone X will be OLEDs, which is a different technology. But nevertheless, you're not going to have OLEDs in this auditorium for many, many years, and maybe never, because of the efficiency of those devices and the lifetime of those devices right now, at least. So this advancement from that brick that cost $1,000 to an iPhone X, iPhone 10, is due to a lot of silicon, a lot of really important engineering and software, of course, but also to more efficient power amplifiers based on 3.5s. So RF semiconductors designed and manufactured by MOCVD reactors is really what drives a lot of this. You wouldn't want to use an iPhone X for an hour and have to go find a charger. I mean, that really wouldn't work for you. You want to have at least 24 hours or more of power. So your power efficiency has to be extremely good, and the power amplifier is a big user of that power. This is what is contained inside that power amplifier, one or more of these. This indium gallium arsenide pseudomorphic high electron mobility transistor, PHEMT. And there's the PHEMT. And this is an HBT, heterojunction bipolar transistor, based again on indium phosphide, all grown by MOCVD. So again, look at your phone today and hit it with a hammer, and what falls out is a bunch of silicon, of course, and a battery. Most of it's battery and display. But really makes that work is this power amplifier that's based on MOCVD devices. How does the mobile industry look like relative to the internet? Well, it's similar in many respects. The 68% compound annual growth rate. The total frequency bands inside a phone has gone dramatically up to 40. Again, these are all RF power amplifier requirements. So you can imagine what's inside the phone in terms of its RF capabilities. Extremely powerful devices with really excellent RF performance. And this is the mobile device RF traffic, as you can see, growing rapidly as well. This is evolution and dynamics of the wireless industry, showing you how the mobile device growth has occurred. Here's 2G, 3G, 4G, LTE versions of the filter content, switching and tuning content, and power amplifiers and other. Here's the power amplifier part. It's the largest part of this other than the filters, which are more or less passive. So the power amplifier is a big part of your cell phone. It's really the thing you rely on the most. I got no signal. I got battery, but I got no signal. I got a display, I got no signal. What's an iPhone good for with no signal? Well, you still take pictures. Well, that's good. You still take pictures. This is a comparison of a technology that's competing, or is in some places thought of as competing. Silicon on insulator, CMOS, for power amplifiers compared to gallium arsenide HBTs. This is from Skyworks. And as you can see, the PAE, the linearity, the losses, integration, die size, and solution cost, pretty much the HBT wins by a lot. So if you're designing an iPhone or iPhone 20, someone's designing iPhone 20 now, you got to think about where I'm going to get my power amplifier. And silicon always ends up being an option because it's so cheap and the technology is so pervasive. But you can't get there from here with silicon, in my view. You have to use 3.5 electronics. Another place you have to use 3.5 devices is in the VCSEL technology, which is part of the upcoming use of optical technologies off-chip, interacting with light, if you will. As you all know, if you have a semiconductor computer, you probably have a mouse or some kind of off device like that if you have a laptop or a desktop. And those mice have VCSELs in them, largely. And so there's lots of places. Here's a VCSEL chip. This is a wafer. Different opportunities for using VCSELs. They're used in printers, laser printers. They're even used in industrial heating because you can make large area arrays of these devices and in cosmetics. Here's an example of a MOCVD grown VCSEL array. For those of you who don't know what a VCSEL is, the vertical cavity surface emitting laser. It looks something like this in terms of layer stack. Photons are generated inside the active region, just like every laser diode you know. But the cavity is vertical just due to semiconductor layers that are formed as a Bragg reflector. So the laser operates from top to bottom by reflection from the Bragg mirror. And you can make large arrays of these. And here's a power device used for industrial heating. So 100% yield on a full 3-inch MOCVD grown wafer. There's literally 20 or more, typically hundreds of layers in some of these devices that are used for this application. Another application is the infrared side of things, which most of us aren't really familiar with, but they're certainly important in medical security, defense, and environmental applications using infrared materials like quantum cascade lasers, for example, which have literally thousands of layers potentially in each laser diode grown by MOCVD. And MOCVD right now is the production technology of choice for most of the VCSELs and the quantum cascade lasers grown today. As we become more aware of our environment and we're able to find solutions to our environmental problems, these types of sensors will become more and more important and more ubiquitous, but they're clearly useful in security and in medical applications right now. Many years ago, again, 40 years ago, this was the world's record solar cell grown by MOCVD. It's a cell I grew at Rockwell in 1977. This is a picture of it. It was quite small, almost a centimeter on the side, but a record at the time. Today, of course, if you buy a solar cell, a lot of them are silicon or perhaps some other material, but most of them on the Earth are silicon, except for the more advanced systems that use what are called concentrators. Concentrator cells are more like this. This is a wafer I grew in 1979. These are individual 1 centimeter cells designed for multiple sun concentrator applications where you focus the sunlight onto a cell so you have 100 or even 1,000 sun concentration. And the reason you want to do that is it's much more effective. You can make a very cheap plastic Fresnel lens that is a meter square, focus all that light down onto a 1 centimeter MOCVD grown solar cell, and get efficiently the power out of that 1 square meter of sunlight. And furthermore, you can take the heat out and use the heat for some energy conversion. So while there are relatively few concentrator cells on Earth generating power in large quantities, virtually all the cells in outer space now are concentrators, are gallium arsenide cells or derivatives. This shows the efficiency versus year for photovoltaic cells made in semiconductors. You can see there's different kinds of crystalline silicon and even amorphous silicon. And these are thin film cells like cad telluride, very cheap to produce, but very inefficient, these green cells here. The multi-junction cells are in purple, and they're based on MOCVD-grown compound semiconductors, and they have the record here, as you can see. Every one of the records in solar efficiency versus year since right in here, 1990, so 1991 was our reference point, have been MOCVD-grown cells with multiple junctions. And as I mentioned, concentrator cells like this exist. There are power grids in the United States that use these, and in Europe. This is a satellite using MOCVD-grown compound semiconductor multi-junction cells. So if you're launching a space vehicle today that's going to be in near-Earth orbit, the power system you choose is photovoltaics, and the cells you choose are multi-junction cells grown by MOCVD. Even something as old as this International Space Station has multi-junction cells grown by MOCVD on it. If you're near Earth and you want to have a very efficient vehicle, you do this. This is one of the cars competing in the World Solar Car Race, which happens every 4 years in Australia, going from the northern part of Australia to the southern part. And many universities compete and many company-sponsored cars compete in this race. The last few winners have been from Holland, actually. And I think most recently, Japan, Holland, and one car from the University of Michigan have been the winners. There's a race this year, so you can watch it on the web. This is an airplane that you probably know about. The Solar Impulse 1 was the first solar-powered airplane to stay up for more than a week. I think this one has gone around the world. And so this is an array of compound semiconductor cells for high efficiency on its wings. Off the Earth, this is a little vehicle that drives around on Mars. Opportunity and Spirit, the Mars rovers launched many years ago by the US. These are compound semiconductor gallium arsenide-based cells grown by MOCVD. So everything we've learned about Mars, from its chemistry to how its dirt works, most recently has come from these rovers based on MOCVD cells powering them. Now, our eyes are well adapted for the visible, and so it's interesting to know where we can make visible light. Historically, we've made it by burning things or lighting up a filament by heating it. But many years ago, long ago actually, people discovered that semiconductors could emit light, visible light. And so today, if you wanted to make light efficiently, the most efficient form of lighting known to man and women is solid-state lighting based on light-emitting diodes grown by MOCVD. And these are some of the examples. This is the visible range. The red, orange, yellow that we see in our traffic signals in cars is Allen gap indium aluminum gallium phosphide quaternary alloys grown by MOCVD. And the blue, green, white LEDs are all indium gallium nitride or indium aluminum gallium nitride quaternary LEDs grown by MOCVD. However, other photon sources are important. I'm showing these infrared ones here, deep infrared ones. around 1.3 to 1.55. This is the technology used in optical fibers. I mentioned the 1.3, 1.5 micron fibers, 1.4 micron sources are this indium gallium arsenide phosphide quaternary grown by MOCVD. And we're starting to make UV devices in the UVA, UVB range by MOCVD as well. These are products that are commercially available, but not yet a large market for them, but they will become a large market because water purification uses devices in this range. Also, some types of printing uses these devices, and curing of plastics uses these wavelength ranges. So that will become an important application. This shows the details of that system that I mentioned, the quaternary indium aluminum gallium nitride system with band gap versus lattice constant. And mysteriously enough, this system covers all photon ranges from 0.7 eV, this is the band gap of germanium in the infrared, to 6.2 eV in the deep UV. And this is solar blind. There are no photons from the sun on the Earth's surface in this range. And these are not visible to us because the human eye response begins around 380 nanometers to about 900 if you're lucky, maybe 800 nanometers. So this quaternary system is unique. It's all direct band gap, and it gives us access to virtually all the photons we need for most of humans' activities, and even things that we haven't yet invented, perhaps. So it's quite remarkable. It has lots of challenges, and Jiahong's going to solve most of those here at KAUST, so you can look to him for the solution for these problems. Today, of course, solid-state lighting is everywhere, and hopefully in this room. This is a stadium in the United States lit by solid-state lighting. What's coming online, though, are not only light for your eyes, but light for your telecommunications. So information can be transmitted by modulating this light beam that's visible, and you can have sort of a local network in this room that could communicate within the room securely, or you could, in fact, have your lighting system connected to the web. So you would use light instead of wireless connections. Since the lighting's here anyway, it's for free almost, if you can modulate it fast enough. So this is a possible application for what's called Li-Fi, light fidelity, if you will, Li-Fi. Also, people are studying the effects of lighting on humans in terms of circadian rhythm. We all have been generated by billions of neurons trained to respond to the sun and the sun cycle. And so it makes sense for our lighting systems inside our environment to respond to the sun cycle that we've come to be evolved toward. Lighting has moved dramatically to solid-state lighting, and that's why those reactors have appeared in Asia to grow LEDs. This shows how the lighting application for LEDs has changed versus year for different applications. Notice general lighting. In 2008, it was virtually unknown for lighting a room like this. And now it's the dominant source of lighting for any new structure will be designed with solid-state lighting, and everything else is growing too, pretty much. LCD TV we'll see, because this LCD TV is being replaced by OLEDs. OLEDs are LEDs, by the way, so it's still LEDs. Just right now, they're not grown by MOCVD, but all of these are grown by MOCVD. And every one of us now wants to control our power, especially in our cell phones, but also electric vehicles. Big power grid systems are distributed, not nuclear power stations or power stations burning fossil fuels in a central location, so they become distributed. It becomes important for all electronics to operate at high voltage. Silicon can't do that efficiently. So 3.5s will become the dominant, probably nitrides, the dominant source of power control in the distributed grid. And so when you plug in your car, you'll actually be plugging into something that is controlled by a gallium nitride power device, grown by MOCVD. All of us have this fascination, most of us at least, with space and space communication and space travel. Clearly near the Earth, and near the sun, we can use that as an energy source. As we go away from near sun, we have to use other power sources, but we still have to communicate. So we have to have some sort of communication, typically RF. Here's a satellite, sort of current generation satellite. All of these bubbles that are shown here basically use 3.5 semiconductors in some form or another, and virtually all grown by MOCVD. Soon, this system will become alive. It's one of the many proposed satellite-based communication systems that will cover the Earth. It's called OneWeb. There are 900 satellites in this constellation, as you can see here. All of those will be using RF power systems controlled by 3.5 devices grown by MOCVD. So soon you won't be worried about whether there's a cell tower near you or not. If you're in the middle of the desert in Saudi Arabia, you can communicate with anyone in Moscow. You call Gorbachev, say hello, how are you, Mr. Gorbachev? He may not answer your phone, but you can still leave a voicemail maybe. So that's good. And obviously cars no longer are mechanical devices. They're all rolling electronic devices. And soon there'll be rolling electronic devices not requiring a driver. So at some point, while I think soon women will drive in this country, it'll be useless because the car will be driving itself anyway. So you won't worry about it anymore. You just get in the car and go. A lot of these things that you see here pointed out are silicon, but really important ones like all the RF sensing, RF transmission of information between vehicles will probably be coming out of 3.5 based RF systems. And certainly the lighting, laser headlights, a lot of this night vision will be 3.5s as well. Heads-up display will be 3.5s. And then there's this next technology of interacting with information. We'll see how this goes, but I believe it'll be 3.5s. A lot of it will be 3.5s because it's the fastest technology we have right now and becomes more efficient as we add more MOCVD reactors to the world. This is a plot of the productivity versus year for electronic devices. Actually, this includes mechanical calculation. This is sort of brute force calculating power. You begin somewhere back here, actually, with Babbage's proposed mechanical computer, and then you move forward to mechanical systems, to the first electronics using vacuum tubes, to discrete transistors, to up here where we have a lot of integration. And eventually, you come to the fact, as I mentioned, that silicon ends up being too slow. You can shrink it to a point, at some point, a transistor may be 1 atom wide, but it probably won't be silicon. It'll be something else. And here's how that's going. This is an analysis that you often hear about what if X technology developed like silicon did. In 1978, commercial flight between London and New York cost $1,900 and took 9 hours. So if the airline industry had been evolutionary like silicon, it would be 1 cent and take less than a second. So this is Elon Musk's idea, right? You're just going to get there in 1 second. General Motors had made, or any car company made cars. Today we're driving $25 cars that got 10,000 miles to the gallon. So this is a very disruptive technology that no other human-made technology has been able to compete with as far as how far it has advanced, how quickly it's advanced, and the impact it's had. And the next generation is not silicon, it's silicon plus 3.5s. Here's a plot of the information processing capability of different systems, beginning with Babbage's invention that never was manufactured. It was too hard even for that technology to be made, and moved along to this was a milestone, the PowerMac G4, the first computer to have more than 1 billion floating point operations per second. An amazing thing to put on your desk at the time. And those of us who were able to buy one, we were sort of proud to have this, even though we didn't use it, right? It was used for internet or word processing. But eventually, as you can see, we're about to the point where we can now beat the processing power of a small rodent. And at some point, we'll beat the processing power of the human brain around 2023. And then somewhere up here, who knows what happens. When your device in your pocket is smarter than you are, what do you do? Of course, that device doesn't think yet, does it? It just does what you ask it to do. So there's still a lot to be done to make this real comparison, because a mouse doesn't need anyone programming it. It's genetically programmed to do all the things it does. We haven't learned quite how to program that efficiently. Nevertheless, I think, again, somewhere in this gray zone, we already have seen it, that 3-5s play an important role. And this is one reason why. This is a plot of the number and length of transistors bought per dollar versus year. And as you can see, things have actually turned over. So silicon has hit the wall. It's really not going to go further in terms of advancing our lives in the sense of being more efficient. And so how do you solve this? This is what's known as the red brick wall in the International Technology Roadmap for silicon. The red brick wall keeps moving because people find solutions to get over the red brick wall. So the red brick wall moves to a different year. But at some point, there's this place where the red brick wall has no solution, and no technology extrapolation can get you across the red brick wall with silicon. So how do you beat this? Well, the way you can beat it is shown here in this Intel slide, showing their technology generations from 2017 to beyond 2020. And somewhere right in here, you see a quantum L35 device. That's the solution, and that's an MOCVD grown device. So I can tell you right now, in a small town in Arizona, there's an Intel plant with MOCVD reactors doing something mysterious, which we don't know, to integrate 3-5s with silicon and to solve this problem of that turnover and the red brick wall. There's other possibility. Here's a nanowire, here's graphene, but no one has a graphene amplifier. No one has a nanowire amplifier yet. So that's your problem. But the interim solution, at least until nanowires and graphene become light emitters and high-speed electronics at terabits for minuscule amounts of power, the interim solution is to take MOCVD-grown quantum well devices and marry them to silicon. So my claim is that Moore's law is coming to an end, and that the only solution is to append 3-5 semiconductor technology to silicon, and that's going to be done through MOCVD, through compound semiconductors. This shows why we need more research, right? There's still a lot to be learned, and here's a plot of the main areas where 3-5s have had an impact and will have an impact, and some of the application spaces. Right now, the global market for compound semiconductor devices is projected to grow to 104 billion by 2020, and demand is expected to grow to 128 by 2025 with a compound annual growth rate of 12.6%, which is pretty remarkable again, and based on probably inaccurate estimates, will probably be larger than this, as we learn to take advantage of compound semiconductors and their functionality with silicon and with the human living space. So here's a cartoon of what might happen of a silicon chip with 3-5s stuck on it. GaN switching devices, 3-5 RF devices, automatic digital control stuff, terahertz detectors, converters, RF modeling structures, photonic link, power amplifiers of various kinds, and LEDs. We don't know if this will ever happen. This is a schematic diagram. We have to solve this problem. But eventually it becomes part of your life. It becomes part of our human environment. It's hard to say whether we'll have chips implanted in our brains, but that's probably going to happen, especially for people with serious deficiencies in either learning or in locomotion. You can activate neurons and motor cells that you couldn't get access to through the biological process. So the home will certainly be filled with this stuff. And my story is that MLC will cover the Earth and make everyone's life better. So thank you for your attention. I'd love to have you come and visit us. Actually, MOCVD already covers the Earth. Here's a picture of the Earth at night taken from the space station and stitched together. You see basically lighting from most parts of the world where there are humans living in high density at least. So obviously it does cover the Earth. You're welcome to come to Atlanta. And we have campuses in Shenzhen and Metz as well, so come visit us anywhere you get close. Thanks for your attention.